The word similar usually just means a little bit the same, but in maths the word similar has quite a specific meaning. Similar shapes are an enlargement or a reduction of each other. So they're in the same proportion and have just been made smaller or bigger, and this holds true even if they've been flipped about or rotated. Now, the key features of similar shapes. The corresponding angles are equal. Now, what do I mean by corresponding? Well, I mean the angles in the same part of the shape are equal. The corresponding sides are also in the same ratio. Obviously, they don't have to be equal because if you've made the shape bigger or smaller by enlarging or reducing it, the sides won't be the same, but they'll be in the same proportion. A scale factor tells you how much bigger or smaller one shape is compared with the other. So we'll have a look at an example to see how you use that scale factor. Now, I've got 3 triangles here drawn in black. Let's compare them and see if we can work out which shapes are similar. Now, what you need to say to yourself is, all right, let's have a bit of a look at the angles and see if they seem the same. There's only 2 angles marked on each triangle, and not 3. Now, do we need all 3 angles to be marked to be sure that they're the same? It turns out we only need 2. Because all of them are triangles, their angles will add up to 180 degrees. So if 2 of the angles are the same in each of them, the other one will be 180 minus whatever the other 2 added up to. So 2 is enough. Now looking at all 3 of these, they all seem to have one angle with one line and one angle with 2 lines. So on first inspection, they all seem to be equal. Next thing to look at is whether the corresponding sides are in the same ratio, and then we'll check whether the angles are in the same place relative to the sides. That's what corresponding angles really means. So the corresponding sides, we've got 3 and 7, a short side and a long side. So close inspection of 6 and 14, you can say, well, hold on a minute, 6 is double 3 and 14 is double 7. So they look like they're in the same ratio. Over here, 30 and 70 looks a lot like 3 and 7, but just 10 times bigger. Obviously, they're not drawn to scale. So how do we compare if they're corresponding or not? Well, the easiest way, especially with a triangle, is to look at what side is opposite which angle. So in this one, the 3 is opposite the 1 line angle, and the 7 is opposite the 2 lined angle. Here, the 6, which we've said 3 is to 6 as 7 is to 14, that works. The 6 is actually opposite the 2 lined angle, not the same place as where the 3 is. So it's got the same angles, it's got sides in the same proportion, but they don't seem to be in a corresponding way. So these 2 triangles are not similar. And in fact, they can't actually exist like that if these angles were working this way. Looking at these 2 angles though, the 30, which is like the 3, is opposite the 1 lined angle. So it looks like the same as this one. And the 70, which corresponds to the 7, is opposite the 2 lined angle. So these 2 triangles are similar. And this one is a red herring meant to trip us up. All right, looking at the blue set of triangles now to try and figure out which 2 are similar. All 3 of them look like isosceles triangles, and we can see that because they've got 2 equal sides, 2, 3, and 4. So we have got no angles to work on here in this picture. We need to really just look at the sides and see if they're in the same ratio. So what we're saying is 2 is to 3 as 3 is to 4, and asking whether that seems right, or 2 is to 3 as 4 is to 6. Now if you write it down like this, 2 is to 3 as 4 is to 6, and see if that looks right, it's exactly the same as when you're making equivalent fractions, or even ratios. You could write this as a ratio, and say 2 is to 3 as 4 is to 6. And sure enough, this is doubled and this is doubled, so they're in the same proportion. Or you could say this is multiplied by 1.5, and this is also multiplied by 1.5. It's the same as when you say 2 over 4 is the same as 3 over 6, isn't it? And you see that those are equivalent fractions. They're in the same proportion. Now what we need to ask ourselves, these seem to be in proportion, so they're similar. Is this one in the middle the same? Well, you can check it by saying 2 is to 3 as 3 is to 4, and having a look at that to see if that looks right. Now it doesn't look right because clearly 2/3 and 3/4 are not equal. So 2:3 can't be the same as 3:4. So this one is not similar to the other two. Now, why were we able to, down here, decide that these two are similar and this one's not, when we didn't know anything about the angles? Well, let's imagine that we were trying to draw both of these triangles and make them have different angles. Would it be possible? It turns out it wouldn't be possible. The reason is, as you go to draw this triangle that has two 2-centimetre sides, imagine your two sides. You can open them up as much or as little as you like because this angle here at the top hasn't been specified. But it sort of has been specified because we need the ends to be joined up with something that's only 3 centimetres long. So as you go to build it, there's only one angle that could possibly go there that opens up the 2 centimetre sides to just the right amount that will make this be exactly 3. Similarly, as you go to draw the bigger triangle with its 4 centimetre sides, they might be twice as long, but also this 3 centimetre part is also twice as long, it's 6, and it will be the exact same angle that you need to open the 4 centimetre sides up to make this be 6. So these angles will automatically be the same. That same sort of arrangement isn't always going to happen with other shapes. Imagine that you had two rectangles and you were trying to decide whether or not they were similar. Now here we just had triangles where if we knew that the sides were in the same ratio, then automatically the corresponding angles were equal. This doesn't hold true back the other way for anything other than triangles. Let's have a look at two rectangles. Let's say one is 2 by 3 and the other is 2 by 7. They're clearly not an enlargement or a reduction of each other, even though all the angles are equal. It fails the corresponding sides in the same ratio. But if we have a triangle that has all the same angles equal, let's label this one 1, 2, and 3, it's actually impossible to make a triangle that has these same 3 angles that isn't similar. And the reason for that is no matter how long you make your base, as soon as you get this angle here on your protractor and make it go up indefinitely, and then no matter how long this is, you put this angle in your protractor at the other end and make it go up indefinitely, that same angle will be the one that's left over at the top. So what are we getting to? Well, for triangles, if you have this, you have to have that. It just automatically works. And if you have this, you automatically have that. You've got a changeover. But with shapes other than triangles, you need to be a little bit careful. You need the corresponding angles to be equal and you need the sides to be in the same ratio to be sure that they're going to be similar.